Welcome back to Inorganic Chemistry. In this lecture, we'll continue talking about models of bonding. Last time we looked at how to do a Lewis structure and talked about formal charges. In this lecture, we'll look at molecular geometry and the polarity of molecules. To determine the geometry of a molecule, we're going to use the valence shell electron pair repulsion theory, which has been modified a few times over the years, but is still a good framework for starting to understand the structure of a molecule. And I've posted a link to your general chemistry textbook table to help you with this. And we'll even use this, even though we start with Lewis structures, this is helpful in looking at symmetry of molecules and molecular orbital theory, because we need to know or estimate what the shape of the molecule is. So first we start out with a Lewis structure, like we saw in the first lecture, and then we're going to count the steric number. The steric number is the sum of the lone pairs and atoms, not bonding pairs, because there could be double bonds or triple bonds, so looking at the atoms or bond groups around the central atom in a molecule. And then once we know the steric number, then we can match the electron pair arrangement from our table, and then to determine the actual molecular geometry, we need to remember that when we look at molecules, we see atoms, we don't see electrons. So lone pairs of electrons are invisible. While they contribute to the electron pair arrangement, they don't show up in the actual molecular geometry itself. And then we also need to note that how the molecule might be distorted from the ideal sort of Platonic geometry. So for example, in terms of VSEPR, we consider that lone pair interactions are stronger repulsion than lone pair bonding pair interactions, which are stronger than bonding pair interactions. And the idea here is that the electron pairs or electron groups, the sterics, these are all negatively charged, and so they want to spread out away from each other as much as possible within the three-dimensional constraints around the central atom. So we'll practice that in class with some molecules, and once we know the molecular geometry, we can talk about symmetry and polarity. And symmetry we'll save for the next chapter, but let's look at polarity now. Polarity of a molecule depends on the molecular geometry, the three-dimensional geometry in the molecule, and we can describe that using the ideal shapes we just talked about, as well as using the rules of symmetry, and the electronegativity, or the polar bonds in the molecule, which come from unequal sharing of electron pairs due to the electronegativity of each element. So for example, we have here in water, we have oxygen-hydrogen bond, and this bond, covalent bond, is polar. Actually, almost all chemical bonds are polar, except for between, say, homonuclear diatomic molecules. So what is the polarity here? Well, it depends on the electronegativity of oxygen versus that of hydrogen. Electronegativity is defined as the ability of an atom within a molecule to attract electrons to itself. And so this is actually, you cannot measure this directly because it's inside the molecule, and the atom of an atom of an element in one molecule may have a different degree of attraction for the electrons than the same element in a different molecule. So every molecule is different. How can we quantify what this electronegativity is? And so to do that, there have been a number of theorists who have come up with different models or scales for quantifying electronegativity. The most famous is the Pauling electronegativity scale. Linus Pauling was a famous chemist in the 20th century who actually won 2 Nobel Prizes, and he devised his scale by considering the bond dissociation energy of diatomic molecules. So, and then characterize the electronegativity as the difference of these bond dissociation energies. So here you have basically an average of the sum of the home nuclear bonds, and then how does that differ from the actual heteronuclear bond strength, and then square root and some fudge factors. So that gives you the differences in electronegativities for the two atoms, A and B, two elements, A and B. And Pauling set fluorine as the most electronegative with a value of 4, and then everything else would be relative to that. So that's empirically determined by measuring bond dissociation energies in molecules. Mulliken had a different approach, which is he looked at the properties of the elements, properties we talked about last chapter, ionization energy and electron affinity. And the ionization energy of an atom plus its electron affinity divided by 2 defined as the electronegativity. Oh, I should point out the Greek chi is the symbol for electronegativity. And to understand this electronegativity scale, we can remember the bond or the energy levels of the electrons in an atom. So here we have the atom, I guess A, right? And then here's the negative atom, negative anion of the atom. So ionization energy is removing electron from the pure atom. And then electron affinity is removing the electron from the anion, and then or electron affinity. So the electronegativity is the average of these two values. So the greater the difference between the atom and the ion, the greater the electronegativity. Allred and Rachau also looked at properties of the atoms, and again looked at concepts that we've already seen. This is the covalent radius within that molecule. This is the effective nuclear charge, so shielding here was calculated, as well as the charge of the electron. And so they came up with a scale for electronegativity. And many other models and scales have been devised over the years. And these three, though, are the most popular. Pauling is by far the most widely used scale. It's the one in your textbook is based on the Pauling scale. And even these other scales, there are fudge factors added in or multiplied in to make their values match the same Pauling scale with fluorine at electronegativity value 4. Okay, so I think for one of your homeworks you are to look at electronegativity trends of the elements in the periodic table But the general trend is that fluorine is the most electronegative, so oxygen next to fluorine is also very electronegative. Hydrogen is less electronegative, and so in this oxygen-hydrogen bond, the oxygen is attracting the electrons more than the hydrogen. So we're going to draw here this attraction of electrons to the oxygen. If electrons are less attracted to hydrogen, they move away from the hydrogen. That leaves a positive charge. Same here on this oxygen-hydrogen bond. And then together you can see, because of the bent molecular geometry, so using the shape of the molecule, we see that this vector and this vector sum to a polarity. This side of the molecule is partially negative, this side of the molecule is partially positive. The molecule is polar. Carbon dioxide, carbon is less electronegative than oxygen. Carbon is less electronegative than oxygen. But in this linear molecule, again we can find the 3D geometry by VSEPR, this vector cancels out this vector, and so carbon dioxide is non-polar. And in class and for your homework, we'll look at more complicated geometries, and we'll learn the symmetry rules that can help us determine this for any molecule. So thank you for your attention. This concludes our simple bonding models for molecules, and we'll look in a couple chapters at a more powerful model, molecular orbital theory, that we'll use throughout the rest of the semester.